Welcome back, class. This is your week 12 lecture, and this week we're going to, again, keeping with slowing down a little bit, we're going to finish talking about testing hypotheses using paired t-tests, and then we're going to move on to the chi-square method that deals with contingency tables. And the next week we will discuss simple linear regression model that allows us to compare relationships. So far in analyzing two sample hypotheses tests, the samples have been independent of each other. Now we're going to shift gears and talk about samples that are paired to one another. Paired samples are where the sample selected from the first population is related to the corresponding sample from the second population. So here are two situations that are somewhat similar, and the question for each of these situations is, are they independent or paired? Are the samples independent or paired? In the first example, we randomly select 20 males and 20 females and compare the average time they spend watching TV. Is this independent or paired? The answer is independent. You have 20 males and 20 females, and you're just comparing across all of them the average time they spend watching TV. In the next selection, we randomly select 20 couples and compare the time the husbands and wives spend watching TV. Is this independent or paired? These are paired because they depend on each other because you're sampling couples. The paired t-test will be used when handling hypotheses that test for data that are paired, like in the second example. When conducting paired t-tests, there are certain assumptions, so just like when we talked about the pooled t-test that we did before, where you have assumptions. The first is that you have paired samples, obviously, so they're not independent, so that's the big difference. And your second assumption is that the differences of the pairs follow a normal distribution. So not the samples themselves, but the difference between the paired samples follows a normal distribution. And or the number of pairs are large, in this case greater than 30. So if it's less than 30, we need to check whether the differences are normal, and we'll see how to do that in a minute. But we do not need to check for the normality of each population. It's just the normality of the difference between the paired samples. When looking at a paired t-test, here are your three different sets of hypotheses that you can have. Again, the null hypothesis is where the mean difference is 0. So here's your null hypothesis here. The mean of the difference. Okay, so the difference between the two paired samples, the difference between those two, and then you take the mean of that difference is equal to 0. So that's your null hypothesis in each case. Your alternative hypotheses are the same as we've talked about before, not equal, so a two-sided test, less than 0, and greater than 0, so left-handed and right-handed, or left-tailed and right-tailed. The t-statistic looks like this equation up here. Degrees of freedom is n minus 1, and n is the value or the number of pairs or the different number of differences that you're looking at, because you're looking at the mean of the difference minus 0. And then divide that by the standard deviation of the difference divided by the square root of n. Your paired t-interval looks like this, where you have the mean difference plus or minus your t-value of alpha divided by 2 times the standard deviation of the square root of n. And again, your standard deviation of the difference is equal to the standard deviation over the square root of n, which is denoted by this, and s bar little d is the standard deviation of the sample differences, as I mentioned before. Now, I know this is always a lot of numbers and you guys get confused when we talk about the actual formulas. Well, let's look at what it looks like. So here we have a data set that has some paired values, and this is an example using drinking water. So there are trace minerals in drinking water that affect the flavor, and an unusually high concentration can pose a health hazard. So this is actually zinc concentration that these data come from. 10 pairs of data were taken measuring zinc concentration in the bottom water and the surface water at 10 different locations shown here. So this is samples that were taken at the bottom of the water column, if you will, and the surface of the water column at these 10 different locations. So this measurement comes from the same location as this one, so they're paired together. Now, this entry here is the difference between these two values. So what you're looking at here is the data that's shown in my RStudio script, and you will notice that there's already a column entitled difference. So I put that in myself. And this is the calculated difference between the bottom and surface levels for each location. This is the actual data that is being tested, and there are two ways that we can analyze this in RStudio, as we will see in just a bit. But first we're going to work this out by hand using the t-statistics so you can see what it looks like. And the question is, does the data suggest that the true average concentration in the bottom water exceeds that of the surface water? The assumptions that we have, again, are whether the samples are paired, and the answer to that is yes. And then the second question is, do we have a large sample size? Well, we have 10, so our n is equal to 10, and this is less than 30, so our answer to the second question is no, we do not have a large sample. So since the sample size is not large enough, it's less than 30, we need to check whether the differences follow a normal distribution, and we can do this in RStudio, as we have done previously. We can perform a normality probability plot. Again, we're looking at the difference column, not the individual bottom or surface in this case. So here is the code that I used. I've changed it up a bit from what we've done previously by calling the data input instead of just calling it data. I've called it water data 2, and I've read it in, so I have my CSV file that had all this information in it, and I read it into RStudio by typing in water data 2 equals read.csv, and then in parentheses the name of my CSV file. Then I made sure to just put this name function in here because I wanted to make sure that the sample labels were correct. So I called them up using the name function. And as you can see under the name function, it told me that the first column is location, then bottom, then surface, then difference, and it has this extra one that was just because of an input error that I did, but you don't have to worry about that right here. Just know that the data value, or the column names, are what I intended them to be, and this is important to do too because as you move forward with your code, remember you have to use the way that it's put into R specifically to call it back up. So like if this was a capital B, you would have to make sure to put a capital B or a lower b in this case. So it's good to just write this out, to have R write it out for you so you know that exactly how R is going to recognize it. And so that's what we did with the name function. From there on, I can move forward to generate the QQ plot using the QQ norm and QQ line functions. Remember, for paired data, we're interested in the difference between the two samples. That's what we're measuring, and so we need to know whether this variable here is distributed normally. And so when we write out our QQ norm function, it's QQ norm, parentheses, then the name of the data file, which I named it water data 2, $, difference, and difference is this column. That's what we're interested in. That function alone will give us the dots, so it plots these values, the sample quantiles versus the theoretical quantiles. And then remember to add your line, the QQ line, the same data, water data 2, $, difference, comma, space, color, COL equals red, and that gives you this line here. From the probability plot, we can conclude that the difference may come from a normal distribution, right? Looks pretty normal to me. Our next steps, well, actually we can start with step 1 now. We can move toward actually analyzing the data now that we know it meets the assumptions of our test. And our first order of business, our step, is to set up the hypotheses. So our null hypothesis is that our mean of the differences equals 0. Based on the question that we had, the alternative hypothesis is that the mean difference is greater than 0. Again, D is defined as the difference between the bottom and the surface, and remember it was already in our file, so we had that down. Step 2 is to write down the significance level, or alpha. This was not clarified in our question, and when it's not clarified, we assume that it is referring to an alpha at 0.05 or a 5% type 1 error. Step 3 is identifying the critical value and carefully writing out what the rejection region is. And so to do this, we need to go to our T table. Okay, we have an alpha. Our alpha is at 0.05. This is a one-tailed test, right? Because it's our alternative hypothesis is greater than 0, so it's a one-tailed test. Basically, that means that we are going to come over here to 0.05, and this is the column where we're going to find our critical value from, because we're looking at a one-tailed test at alpha equals 0.05. We need to know our degrees of freedom. Our degrees of freedom are equal to 9 because there are 10 groups. Degrees of freedom are defined as n minus 1, so 10 minus 1 equals 9. So if we come down this column to the row of 9 degrees of freedom, I have it highlighted here. This means that our critical value is 1.833. So we can write that out like this. So we know our alpha, our degrees of freedom are 9. So our critical value at 0.05 equals 1.833. This means that our rejection region can be written out like this. T is greater than 1.833. So any value that we get from our test statistic, if it is greater than 1.833, means that it lies in our region of rejection and we can reject the null hypothesis. So we're going to calculate this out for step 4. We're going to compute the value of the test statistic by hand. Here's our formula. Again, remember this is for a paired t-test. We enter in our values here. This is our mean difference. This is our calculated standard deviation. And if you don't want to calculate those out by hand, your data is already in RStudio because of the QQ plot calculation. So you can calculate those out pretty quickly. Mean, parentheses, water data 2, $ difference will give you the mean, 0.804. SD is the function that you use to calculate standard deviation from a group of data. Here's our group of data, and here's our standard deviation, which is what we put here. And you know our n value to calculate or the formula to calculate out your t statistic for a paired t-test. In this case, our value is 4.86. That is step 4. Step 5 is to check whether the t-statistic falls in the rejection region and determine whether to reject the null hypothesis. So with a critical value of 1.833, as we determined in step 3, this is a right-tailed test because we are looking at a greater than. Our alternative hypothesis was that the mean of the differences was greater than 0, so that means it's a right-tailed test. So our t-star value, or our calculated t-value at 4.86, is greater than 1.833, which is our critical value. So what does this mean in terms of rejecting or failing to reject the null hypothesis? It means that we reject the null hypothesis because our calculated t-statistic, 4.86, is greater than 1.833, which means that it falls within the rejection region, so we reject the null hypothesis. The last step is step 6, which is to state the conclusion in words. So rejecting or failing to reject a null hypothesis is not a conclusion. That is only the previous step of identifying what this test statistic tells you about the question that you had. So writing a conclusion or making or stating a conclusion in words means you take what that means in context of whatever the original question was that you're asking with your test statistic. So our conclusion for this, so we've already rejected the null hypothesis, that was step 5. So now our conclusion could be something like at alpha equals 0.05, we conclude that on average, the bottom zinc concentration is higher than the surface zinc concentration. Now I just want to take a step back a little bit because through the homework that you guys have had, it seems like some of you are still a little confused. Once you start step 4 and work your way through to step 6, there's a little bit of confusion as to what the different values mean. So if I leave this up here for just a second, actually let me go back just a second and let's come back to our original hypothesis. So our original null hypothesis is that the mean difference is equal to 0. This is actually what the t-statistic is testing. And so if you reject this, which is what we did because our t-value that we calculated, which was 4.83, which is 4.86, is larger than our critical value. It falls within the rejection region. And because it falls within the rejection region, that means that we reject it. It's in the rejection region, we reject the null hypothesis. So it means that we're rejecting this part here. When that happens, it means then that you can use your alternative hypothesis as your conclusion. So it means that the mean difference is greater than 0, which in this particular case means that the bottom zinc concentration is higher than the surface zinc concentration because of the way that we set up the data based on the original question that was asked for this test. All right, so that is a paired t-test. So when the samples are paired to one another, like they were here, and this is calculating it by hand. We did use RStudio a little bit when we calculated the normality plot, as well as you can use it, as I mentioned, and it shows here, to calculate some of the descriptive statistics like the mean and standard deviation that you need to calculate the actual test statistic. What you can also do is use RStudio for the entire process. So let's go. Here is my view from my RStudio here with it all worked out. Okay, so this, so far, if you look down here on my console, this is what we've already done. So I read in the data, I read the names, I did the QQ plot, the QQ norm with the QQ norm function, and then added a QQ line, and that's how we got this QQ plot here. And then I also used the mean and standard deviation function to calculate the mean and standard deviation that we used just a second ago. So if you move up here into my R script where I like to write and save the coding that I used for each experiment, you'll notice up here that there's a lot of untitled scripts. But here's one gradepoint.r. Remember we did this in the last lecture. We did an RStudio on gradepoint. And here's the water data saved over here. It's a different version of data, and then I will always be able to pull that up so I'll know exactly what code I used. Okay, so here we've read in all of our data, and there are two ways that you can run a paired t-test. And I have them both, the codes written both right here, but I'm actually going to exit out of PowerPoint really quick, and I'm going to go over to my RStudio. Okay, so here we are in RStudio, and notice that it's fairly empty. We'll just assume you can ignore the stuff down here at the bottom. So I'm going to start up here in my R script. I like to write stuff up here. You can do it wherever and however you feel comfortable. But I'm going to go ahead and start back from the beginning. So I already know, because I've been working in this, that the working directory is where I need it to be. It's pulling information off of my desktop. And so I don't need to start with the set working directory because I already know that it's there. I've already checked that. Just remember that you may need to do that if you're working on a new computer or something, or on a university computer or something, that you always want to check or get your working directory to find out where R is, or RStudio is reading the data from. So I already know that, so I'm going to move right into this, and I'm going to go ahead and keep this name that I started before, so water data 2. is going to equal the data I'm about to read in. So read.csv, parentheses, the name of the file I'm reading in is drinkingwater.csv. So remember, it's not going to do anything on my terminal unless I hit command return. And once I do command return, or you can type it down here on your own if you want, down on your console. It's really up to you, but now you see that it's put it in blue. It's added. I have a new cursor here, but also more importantly, my data is right up here. Okay, so it's in this environment, this global environment here, all the data. Water data 2 is what I just read in. If you want to, you can just click this and it will show you what your data looks like. There it is. Here's that weird X column that I told you not to really worry about. It doesn't really matter. Okay, so let's come back here. So we've read our data in. The next thing that I told you that I did before was to just make sure that then the labels were right. You can do that by viewing the data like we just did. So looking at the data, here are those label columns or those name columns. You can also use this name function. So names is going to give you that if you, again, command shift on a, or command return, sorry, on a Mac will run this for you. And again, location, bottom, surface, different, and X. So just like I showed you before. So just to walk through all the things we did before, we can do our normality plot. Water data 2, difference. That gives you your normality plot. We want to add a colored line to that, and I want it to be red. And so we do that. So remember, if you just hit enter here, it's just going to go to the next line. So again, remember, you can work down here. This just allows you to edit the code if you need to, like if you mistype something and it doesn't work. So here's your QQ plot. So we had already worked that out before. Again, remember, you can calculate a mean. See, we're interested in the difference. So there's our mean. Down here of 0.84, you can do that with standard deviation. Remember, as soon as you start typing, it then pulls up a menu if you want. So again, oops, I didn't hit command return. So here's your value down here. So those are the values that we'd already done. Now we're at the point where we want to do our paired t-test. So, oops, I'm just going to come back up here and I'm going to make a space. Now, there are two different ways that you can run this paired t-test. Both of them start with the function t-test. So just like you did in the last lecture, we talked about pooled t-test. Remember, that's the default, okay, a pooled t-test. We're going to come back to that in just a second. But what we've talked about so far, like we did our normality plot on the difference between the means of the bottom and surface, right? So here's our data. So you have these values that were taken at the bottom of each location, these values that were taken at the surface of each location. And when you're doing a paired t-test, the value that you're running the analysis on is the actual difference, okay? So it's a calculation that you have to make. You didn't go out and sample this difference. You calculated it from your two sample variables that you have here that are paired together. Okay, they're paired together, you take the difference. It's this difference column that you're running the stats on in a paired test. Okay, so if we come back here, so then our t-test, one way to do it, to set it up, is to say t-test water data 2, and the variable of interest is here. So you're basically running a one sample t-test here. Okay, so let's go command enter. Boom, this is what we get down here. Here's our one sample t-test. We ran it only on the variable difference. Running a one sample t-test on that variable is the same as doing a two sample t-test paired, but when you do that, you have to tell it that the data is paired. So I'm going to show you that in just a second. But what I want you to recall, if you come and you look at these values down here, here is the calculated t value from your t statistic that we did by hand a second ago, remember? And our value that we calculated was 4.84 or 4.86, sorry, which is right here. Okay, here's your degrees of freedom of 9, which we had calculated. The only thing this doesn't tell you is what the critical value was in the rejection region, but what it also tells you, which is what you're interested in effectively, right, is that you have a significant level. Your p-value is 0.0089, and this tells you that you reject the null hypothesis. So the same thing that you calculated by hand. So that is running a one sample t-test on just the difference value. Now you can set this up, I mentioned a different way, so t-test, but instead of setting it up as a one sample t-test, okay, we're going to use our bottom, water data 2, and surface, and then we're going to tell it that the data are paired. So here are your two data points. And so if you're doing this a shortcut method, and let's say you already knew, or you had more samples than, so in this case our n was 10, so it wasn't large enough, so we had to test for normality, which meant that we had to do the calculation to figure out what the difference was so that we could test for normality of that data. Okay, so hopefully you're still following me on that. And since we're not calculating this by hand, if the value, if your n had, say, been 50, say you had 50 locations, you wouldn't have had to have conducted this, it was paired, and your n is large enough that you can make that assumption of normality. So you could have skipped right to the t-test, and you wouldn't have had to have calculated the difference. And so running a t-test on the difference isn't something that you would necessarily do unless you wanted to go back and calculate the difference. So what you could do is run a two-sample t-test, but a paired test, and this is how you would set it up with your two values, bottom and surface, and paired equals true. And when you command enter and run that script, you get the exact same analysis. So even though it's a paired t-test, so here are your two outputs. Here's the first one we ran, the one sample t-test, where we just did it on the variable difference. In the paired t-test, we're doing two sample t-test on the bottom and surface data, and it's running a paired t-test. And look, the calculated t-statistic is exactly the same as it was for the one sample test, 4.86, same degrees of freedom, same exact p-value. So you can set it up either way. It really just depends on whether or not you have to calculate that extra column for difference. So it really depends on what your overall sample size is. These are the two different ways that you can set up a paired t-test in RStudio. So pretty simple. It gives you the exact same thing as if you had calculated it out by hand. So those are the two different ways that you can run it. Here it is again, okay, on this slide of just the two different ways that you can run the paired t-test. Now the question is, what if we accidentally run a two-sample t-test, treating the samples as independent because we didn't recognize them as paired? So what if we ran the script that looks like this, of what we did last week, where we're running a two-sample t-test. Okay, so that second way we ran it, so t-test, and then you have your two samples here, bottom and surface, but you forget or didn't realize that these were paired samples, and you run it as the default. So the default t-test is that pooled, right? It assumes that the data are independent. And so since we didn't tell it that paired equals true, it's going to run this kind of default Welch two-sample t-test. And look what happens. So here are your two data points. So the same two data points that we used in our last analysis where we did tell paired equals true. But this time, look what happened to our t-statistic, 1.29. Look at our degrees of freedom, 17.779, because it's not calculating the degrees of freedom based on all of those samples being paired together. And so our p-value then ends up being 0.214, 3 because this value is not falling in the rejection region based on the critical value. So, in other words, we are not able to reject the null hypothesis, and this demonstrates the importance of distinguishing the two types of samples, so whether they're independent or whether they're paired. Also, it's very wise to design an experiment efficiently whenever possible, where you're laying these things out and making it very clear whether your samples are taken from an independent source or they're taken from a paired source, and that you set up your test statistics accordingly. For now, let's recap what we've discussed thus far in this course and mention what remains. The fundamentals of sampling distributions for the sample mean and proportion we talked about a few weeks ago. We've illustrated how these sampling distributions form the basis for estimation, so when we talked about confidence intervals, and significant testing for one mean or one proportion. That was a few weeks ago. Then we extended the discussion to analyzing situations where you have two variables or two samples, one a response and the other an explanatory one. When both variables were binary, we compared two proportions. When the explanatory was binary and the response was quantitative, we compared the two means. Next, we will take a look at other methods and discuss how they apply to situations where both variables are categorical, with at least one variable being not binary. This is the chi-square test of independence, where both variables are quantitative, and as well as where both variables are quantitative, and we will look at linear regression, and we'll do that next week. In this particular lesson now, we will examine relationships where both variables are categorical using the chi-square test of independence. In the case where both variables are categorical and binary, we will show/illustrate the connection between the chi-square test and the z-test of two independent proportions. Going forward, keep in mind that this chi-square test, when significant, only provides statistical evidence of an association or relationship between the two categorical variables. Do not confuse this result with correlation, which refers to a linear relationship. So it's an association, not a correlation. The primary method for displaying this summarization of categorical variables is called a contingency table. When we have two measurements on our subjects that are both categorical, the contingency table is sometimes referred to as a two-way table. So you can see it either way. This terminology is derived because the summarized table consists of rows and columns. In other words, the data display goes two ways, where the rows represent the levels of the explanatory variable and the columns the level of the response variable. And it can look something like this. So what you see in black here are two variables. So these are your row levels. So they're the level of the explanatory variables. And these are the variables or the descriptions of the response variables. And so here you have two different groups, the Democrat or Republican, and then you have three different response categories. Okay, so this is what a contingency table or a two-way table represents. It means that you have both rows and columns identified, and that's why it's called a two-way. The size of the contingency table is defined by the number of rows times the number of columns associated with the levels of the two categorical variables. The size is noted by little r times little c, where little r equals the number of rows of the table and little c is the number of columns. Wherever a count occurs is called a cell. So this would be considered a cell. Thus, the size of a contingency table also gives the number of cells for that table. Caution: as we will see, these contingency tables usually include a total row and a total column, which represent the marginal totals. This is what is seen in gray here, and that's why I actually have them in gray, because they are not part of the overall table. They're marginal totals. The total count in each row and the total count in each column do not include these marginal totals. So this total row and total column are not included in the size of the table. The size of the table refers to the number of levels to the actual categorical values in the study. So this table here includes data from a random sample of 500 U.S. adults. This is the overall total here, questioned regarding their political affiliation and opinion on a tax reform bill. The size of this particular table is 2 by 3. This is a 2 by 3 contingency table, not a 3 by 4. It only counts the data, not the labels, and not the totals. We define the party affiliation as the explanatory variable and opinion as the response because it is more natural to analyze how one's opinion is shaped by their party affiliation than the other way around. From here, we would want to determine if an association or relationship exists between political party affiliation and opinion on the tax reform bill. That is, are the two variables dependent? A statistical method of choice for this particular type of question is the chi-square test of independence. So the real question that's being asked here is, are these two variables, the explanatory and the response variable, are they dependent on each other? And that gets us to our hypotheses and how you set up hypotheses for chi-square tests of independence. So how to test the independence of two categorical variables. It will be done using this method called the chi-square test of independence. I'm sure you've heard of it before. I know we talk about it in 123 when we talk about frequency distributions. As with all prior statistical tests, we need to define null and alternative hypotheses. Also, as we have learned, the null hypothesis is what is assumed to be true until we have evidence to go against it. In this lesson, we are interested in researching if two categorical variables are related or associated. In other words, are they dependent on each other? Therefore, until we have evidence to suggest that they are, we must assume that they are not. This is the motivation behind the hypothesis for the chi-square test of independence. Well, the null hypothesis. In the population, the two categorical variables are independent. Okay, so this goes back to this assumption that until we have sufficient evidence to suggest that they are related or dependent, we must assume that they are not. So the null hypothesis for chi-square is that the two categorical variables are independent of each other. So that therefore makes the alternative hypothesis that within the same population, the two categorical variables are dependent on each other. Note, there are several ways to phrase these hypotheses. Instead of using the words independent and dependent, one could say there is no relationship between the two categorical variables versus there is a relationship between the two categorical variables. The important part is that the null hypothesis refers to the two categorical variables not being related, while the alternative is trying to show that they are related. Once we had gathered our data, we summarized the data in the two-way contingency table. So I'm just pulling this over from the previous slide. This table represents what we call the observed counts and is called the observed counts table, or observed table as noted here. This contingency table represents the observed counts of the party affiliation and opinion for those surveyed. The question then becomes, how would this table look if the two variables were not related? That is, under the null hypothesis that the two variables are independent, what would we expect to find in our data if the two variables, i.e. party affiliation and opinion, were not related? So to do this, we need to find what is called the expected counts table, or simply the expected table. This table displays what the counts would be for our sample data if there were no association between the variables, and it looks like this. So once we have the observed counts, we need to compute the expected counts under the null hypothesis that the two categorical variables are independent. This is done using the marginal totals and overall total to compute expected counts for each cell in the table. In other words, to find the expected count for each cell in the table, we multiply the marginal row and column totals for that cell. So 285 in this case, which is the marginal total for this row. Okay, so there's 285, 285, 285. You multiply that by the column total. So 202 in this case, 150 for this one, 148 for that one. And then you divide it by the overall total, which is 500. So that's this value here. You do that for each cell. Okay, so this one is 215 because of that value, and 202 because of that value. They're all divided by 500. This gives you the expected count. So to demonstrate, here's the table and all of those values. So these are now your expected values. So these are the observed values. For Democrat in favor is 138 compared to the expected value for Democrat in favor is 115.14. To better understand what these expected counts represent, first recall that the expected counts table is designed to reflect what the sample data counts would be if the two variables were independent, meaning that they were not dependent on each other. Taking what we know of independent events, we would be saying that the sample counts should show a similarity on opinions of tax reform between Democrats and Republicans. If you find the proportion of each cell by taking a cell's expected count divided by its row total, you will discover that in the expected table, each opinion proportion is the same for Democrats and Republicans. That is, from the expected count, 0.404 of the Democrats and 0.404 of the Republicans favored the bill. 0.3 of the Democrats and 0.3 of the Republicans are indifferent, and 0.296 of the Democrats and 0.296 of the Republicans are opposed. The statistical question becomes, are the observed counts so different from the expected counts that we can conclude a relationship between the two variables? To conduct this test, we compute a chi-square test statistic where we compare each cell's observed count to its respective expected count. This chi-square test statistic is calculated as follows. Here is the formula. So x raised to the 2 with a star is what we refer to as the chi-square value. And it's the sum of the observed minus the expected of each individual squared divided by the expected of that individual. And you sum all of those together. And I'll show you what that looks like in a minute. As we have done with other statistical tests, we make our decision by either comparing the value of the test statistic, so whatever value we get here, we compare that to a critical value using the rejection region approach, or by finding the probability of getting this test statistic value or one more extreme using the p-value approach. The critical value for chi-square test is shown by this here, so x raised to the 2 to the alpha, so whatever your alpha is, usually 0.05. And the degrees of freedom are calculated like this: the number of rows minus 1 times the number of columns minus 1. While the p-value is defined by this, your chi-square value greater than your observed test statistic for chi-square, or your chi-square statistic, with, again, your degrees of freedom being the number of rows minus 1 times the number of columns minus 1. So in this case, our degrees of freedom are there 2 rows minus 1 times 3 rows minus 1 gives you a degrees of freedom of 2. So let's calculate the critical value first. The degrees of freedom are 2. We're going to assume alpha equals 0.05. So in order to identify what our critical value is, we have to consult our table. So in this case, it's not the t-table or the z-table. There's a specific chi-square table that is now on Canvas for you. Or you can just Google chi-square distribution table and you will find the same table on Google, just like you can do with a t-table or a z-table if you misplace it. So we know our degrees of freedom are 2. So here on our table, go down degrees of freedom of 2. So now we're looking at this row here. We move across until we get to an alpha of 0.05. So our chi-square critical value is 5.99. Okay, so this is what a distribution for a chi-square looks like. The chi-square distribution is skewed to the left, so it looks like what's drawn here. And what we have just done is, again, our alpha was set at 0.05. So remember, this is a right-tailed because we're looking at a greater than. That was what our alternative hypothesis was. So our critical value is right-tailed here. So whatever our critical value is, it defines this region, which is based on our degrees of freedom as well as our alpha setting, which is 0.05. So what you see in red here is our rejection region. Our critical value as defined by degrees of freedom and alpha value are 5.99. So what this means is that our critical value for this test is 5.99. Remember, that defines this line right here. So everything on the right side of this, or greater than this critical value, falls within the rejection region. So now we're going to calculate our test statistic. Remember, the chi-square is calculated by the sum of observed minus expected, square that, divide by the expected value, sum all of those together. It looks something like this. So if you go back to our table of expected here, these are all of your expected values. Okay, this is your expected value. These are your observed values. They're the values that you utilize in your calculation for the chi-square statistic. And this is what it looks like when you map it all out. So here are your 1, 2, 3, 4, 5, 6 different values. You had 6 cells. You add all of those together. So this is for your very first cell. This is for your second cell, your third cell. These are all of the Democrat values, I believe. These are all of the Republican values, the 3 in a row. You sum them all together and you get your chi-square value of 22.15. When you compare that value to our critical value, which was just identified in the last step as being 5.991, our chi-square value is 22.152. It obviously falls to the right of this line here as it is much larger than 5.991. So what does that tell us? It tells us that our chi-square value falls right in the rejection region, or the red section in our rejection region at alpha 0.05. And given this, we know that we can reject the null hypothesis that political affiliation and their opinion on a tax reform bill are independent. Okay, this is our chi-square value compared to our critical value. It's larger than the critical value. This places it in the rejection region. Therefore, we can reject the null hypothesis that political affiliation and their opinion on a tax reform bill are independent. And this means that we can therefore conclude that they are dependent, that there is an association between the two variables. Okay, this is working it out by hand. We can also do this in R. And so we're going to take a look. Here is a breakdown of how you do that in R, but we're going to actually move over to R and work it out so that you can see what it looks like, because it is reading the data in is a little bit different. And so we're going to move on over to our studio and do the coding for input and running a chi-square now. The first thing we're going to do is put in our values. So I just copied and pasted these from the Excel file that would have the table in it. Okay, so if we go back here, look at here's our table, right? So what I did was just copied the 6 values that make up the values that are important for our chi-square test. and I just pasted them in here. Now, they're not in any format that RStudio can use at this point. We need to actually read them into RStudio, and so what we're going to do is we're going to read them in, and by doing that, so I'm going to name this data politics, we'll call it politics data equals, and then we're going to build a matrix. And to do this, you put matrix parentheses C, that tells it that your data is coming up. And then we're going to put in our values. So you can just type them in like I'm doing here, or you can copy and paste and then just make sure that it's clean in the format that you put them in. Does that look right? 138, 83, 64, 64, 67, 84. So hopefully you'll notice I put one row in and then I put the next row in. And so the important thing that we're going to do after that is tell RStudio that we put the data in by row. And then we're going to tell RStudio how many columns there are, because there's 1, 2, 3 columns. So by reading the data in this way, so you're telling it to put it at build a matrix, here's the data, the values, and these values are in here by row, and there are 3 columns. So RStudio knows that to read this going 1, 2, 3, next row, 1, 2, 3. So let's go ahead and Command Enter. So I ran that. So I built our politics data. It's up here. Okay, we can click on this if we want to see it. So it looks like that. There's our data. It read it in. Okay. The next thing we're going to do is tell RStudio that these columns have names. So columns have names for politics data, and they equal, you want to put them in order. And oppose. Okay, so those are our column names. And if you don't remember those, so come back, if we come back and look at our actual table, here we go. So here's our values. Our columns are named favor, indifferent, and oppose. Favor, indifferent, and oppose. We now labeled that. So once you've labeled it, you can go back in and you can say, okay, politics data. So see, it's entered those columns now into our politics data. And our rows have names also. So row names. And these are Democrat and all right, so now if we look at our data table, they are all in there. All right, so we've now built our matrix, our data table, our contingency table. If we want to look at that data, then you can just type the name of it and it'll show you down here in the console. And what we are doing in RStudio now is running a chi-square test, right? And this is how easy it is. Politics data. And boom. Oh, I misspelled it. So this is the good thing about using the R script up at the top, is I can go back up here. That should be a Q, not a P. So chi-square dot test. And there it is. So here is our Pearson's chi-square test. Here are our values. Our chi-square values, 22.15, just as we calculated before, degrees of freedom 2. Our p-value is very low, 1.54 times 10 to the negative fifth. We can come to the same conclusions that we did here. We can reject the null hypothesis. Again, our RStudio came up with the same chi-square value. That tells us that we can reject the null hypothesis, that political affiliation and other opinion on a tax reform bill are independent. We conclude that they are dependent that there is an association between the two variables. You can do it by hand or you can do it by using RStudio. You get the same values. Okay, so now let's do another example, but this time I want you to try it by yourself. I will post my data on Canvas for you to check your work with. Practice makes perfect, right? So for this example, the students in the class just learned in their biology class that pill bugs use gill-like structures to breathe oxygen. The students hypothesized that the pill bug's gills require them to live in wet environments for their survival. To test this hypothesis, they wanted to determine whether pill bugs show a preference for living in wet or dry environments. The students placed 15 pill bugs on the dry side of a two-sided choice chamber and 15 pill bugs on the wet side of the chamber. 15 minutes later, 26 pill bugs were on the wet side and 4 were on the dry side. The data are shown in the table here. The experimental hypothesis states that pill bugs' gills require them to live in wet environments for survival. The experimental prediction is that if you place pill bugs in a two-sided chamber that is dry on one side and wet on the other side, they will show a preference for the wet side. Make sure you identify what the null and alternative hypotheses are. You can use RStudio, but be sure to also work through how to identify the critical value and set your rejection region so that you understand what the p-value that RStudio gives you means.